Hey everyone, welcome back. Ready for another deep dive? Today we're tackling suffix trees.
Suffix trees, yeah, they're pretty cool. Super useful.
So for those who might not be familiar, suffix trees are like, oh,
Well, think of them as a super efficient way to index strings. Like, imagine a GPS, but for finding any sequence of characters within a huge chunk of text.
a GPS for text. I like that.
Mm.
So we're not just talking theory here. These things have real-world uses.
Oh, yeah, absolutely. They pop up everywhere. Bioinformatics, suffix trees, search engines. Suffix trees, again, they're kind of a big deal.
So how do they actually work? What's the basic idea?
Well, at their core, a suffix tree stores all the possible suffixes of a given piece of text. So let's take a simple word like apple.
Apple. Okay.
Right. So our suffix tree would need to include apple, then peel, and finally just E. All the endings, basically.
Wow. Yeah, that's a lot of endings for just one word.
Exactly. And imagine if we were dealing with, like, an entire book or a whole DNA sequence, storing all those suffixes directly. That would be a nightmare, computationally speaking.
Like trying to find a needle in a haystack, but the haystack is made of needles?
Yeah, pretty much. That's why we need to get clever with compression. Instead of storing each suffix individually, we use this kind of cool system of nodes and edges and index ranges.
Compression. Okay, I'm intrigued. How do we compress a whole bunch of suffixes?
Imagine the suffix tree as a sort of branching structure. Each edge represents a chunk of our original text, and the nodes are like intersections where those chunks branch out.
I'm picturing like a family tree, but for words.
Yeah, kind of. And instead of writing out the entire substring on each edge, we use index ranges. It's like saying this edge represents the characters from position 2 to 5 in the original text.
So we're pointing to the location of the substring, not writing it out in full. Clever.
Right. And to make sure that every single suffix has a unique path from the top of the tree, we use a special symbol. Usually it's a $ just tacked onto the end of the text.
Like a little flag to mark the finish line, so no suffix accidentally becomes part of another one.
Yep, exactly. But even with all this compression, building these suffix trees can still be quite the task.
I can imagine. There must be some pretty complex algorithms involved.
Oh, there are. And the most famous one, the real workhorse, is called Ukkonen's algorithm.
Ukkonen's algorithm, huh? Sounds pretty intimidating.
Maybe a little, but it's actually quite elegant once you get to know it, and it's the key to building suffix trees efficiently.
Okay, so it's like having a master builder for our suffix tree. What are the tools in this algorithm's toolbox?
Well, it mainly uses these 3 main operations. It's all about adding new leaves for those unique suffixes, extending existing branches when possible, and creating these special shortcuts.
Shortcuts in a tree. I'm not sure I follow that one.
Yeah, it's a bit tricky to picture at first. These shortcuts, we call them suffix links, and they're what make Ukkonen's algorithm so efficient. They basically connect different parts of the tree, allowing the algorithm to sort of jump around without having to retrace its steps every time.
So it's like having a secret passageway in our word tree.
Yeah, a secret passageway that saves a ton of time.
I'm already starting to see how this could get really powerful. But how does the algorithm know when to use which operation?
That's where another clever concept comes in, the active position. Think of it like a cursor, keeping track of where we are in the tree as we add each character.
So it's guiding the algorithm, telling it where to go and what to do next.
Exactly. The active position is constantly being updated based on the current character and the structure of the tree. It's really the brains of the whole operation.
This is fascinating. We've got these 3 operations guided by this active position, and then those suffix links, like hidden tunnels, making everything super efficient.
You're getting it. It's all about working smarter, not harder, right?
Absolutely. But I think to really grasp the brilliance of this Ukkonen's algorithm, we need to see it in action.
You're right. Let's do that. Ready for an example?
Bring it on. I'm all ears.
All right, let's go with banana, classic. It's simple enough to follow, but still shows how things work.
Banana. Okay, so we're starting with an empty tree, right? Like nothing there yet.
Yep, totally empty. Our first character is B, so we add a leaf node for B. Remember, that $ is our end marker.
Right, the end marker.
Yeah.
So we've got B hanging out there. What's next?
Next comes A. It's a new character, so we add a new branch right from the top and create a leaf for A.
Got it. So far, so good. 2 characters, 2 branches. But things will get more interesting when we hit the repeating letters, right?
Badass. The next character is N, new again, so new branch, new leaf, and $. But now, pay attention to the active position. It's sitting at the end of that N branch.
Like our little cursor is pointing right there, ready for the next step.
Yeah, exactly. And here comes another A. Now, instead of creating a whole new branch, we just extend that existing A branch to represent Anna. The active position moves along with it.
Ah, so we're reusing a part of the tree instead of creating a duplicate. That's where the compression starts to shine.
Exactly. And this is also where we add our first suffix link. See, we have an internal node now for A. We need to connect the previous N node to this A node with a suffix link.
Hold on, why? I thought suffix links were for suffixes that differed by the first character, like, Nana and Anna.
They are, but think about it this way. If we started building the tree from scratch, but used the string anana this time, the first thing we do is create that A node.
Ah, I see. So the suffix link is basically saying, hey, we already built this part before, starting from a different point.
That's the idea. It's all about optimization. Okay, back to our banana construction. We have another N coming up. Thanks to that suffix link, our active position can jump straight to the A node. No need to start from the top again.
A shortcut. That saves so many steps.
Right. Efficiency is key. So we extend the existing Na branch to become Nana, active position, tagging along.
Okay, I think I'm starting to get the hang of this. We add leaves for new suffixes, extend where we can, and use those suffix links to make things faster. What happens when we get to the end of the word, though? There are still some suffixes missing, like na and just a on their own.
Great question. Once we hit that final $sign, Ukkonen's algorithm does one final pass through the tree, adding those remaining suffixes as leaves.
So we make sure every single suffix, even those that are part of other suffixes, gets its own spot on the tree. No suffix left behind.
Yeah, precisely. It's all about completeness. And with that, our suffix tree for banana is finished.
Wow, that was amazing to see in action. It's like a perfectly orchestrated dance, everything happening just at the right time. But I'm still curious, why is this particular algorithm so efficient? What makes it so special? So we've seen how it works, but what makes Ukkonen's algorithm so efficient? It seems like there's a lot going on under the hood.
Right. It's surprisingly elegant, actually. One of the biggest things is that it achieves what we call linear time complexity.
Linear time complexity. Okay, what does that mean exactly? I'm a bit rusty on my algorithm analysis.
Basically, it means that the time it takes to build the tree grows proportionally to the length of the text. So if you double the length of the text, it takes roughly twice as long to build the tree. No matter how long the text gets, the algorithm can handle it efficiently.
So it scales really well. That's important, especially for those big data sets you mentioned earlier.
Exactly. And a lot of that scalability comes down to the suffix links we were talking about. They let us reuse parts of the tree we've already built, which saves a ton of time.
So the more repetition in the text, the more useful those suffix links become.
Exactly. It's like taking shortcuts through a maze. And on top of that, the three operations themselves, adding leaves, extending branches, and creating suffix links, they can all be done in constant time.
Constant time, meaning they take the same amount of time no matter how big the tree is.
Yep, that's the idea. It's like each step is a small, fixed task, no matter how complex the overall structure gets. And of course, the active position plays a huge role too.
Right, that little cursor, always keeping track of where we are.
Exactly. By using the active position cleverly, we avoid a lot of unnecessary searching and backtracking. It's all about working smarter, not harder.
So it's not just the individual operations, but how they all work together, guided by the active position and those suffix links that makes Ukkonen's algorithm so powerful.
You got it. It's a beautiful symphony of efficiency. And the best part is, this efficiency has a huge impact on all those real-world applications we talked about earlier.
Right, like those massive search engines and DNA databases.
Exactly. Imagine trying to handle those data sets with a slow, clunky algorithm. It would be a nightmare. But Ukkonen's algorithm lets us build these incredibly complex suffix trees in a very reasonable amount of time. It's a real game changer.
So suffix trees are more than just a theoretical curiosity. They're a practical tool that's used to solve some really important problems. And it's all thanks to this elegant algorithm.
Absolutely. They give us a whole new way to analyze and understand strings and patterns, and the possibilities are pretty much endless. They're used in everything from plagiarism detection to spell checking, data compression, even artificial intelligence.
Wow. It's amazing to think how much we can achieve with a few clever ideas and some efficient algorithms. Well, dear listeners, I hope you've enjoyed this deep dive into the world of suffix trees and Ukkonen's algorithm.
It's been a pleasure, and who knows, maybe this will inspire some of you to explore the world of algorithms and data structures further. There's a whole universe of fascinating concepts out there just waiting to be discovered.
So keep exploring, keep learning, and keep diving deep. Until next time, happy coding.